Hi again, welcome to lesson 4. So far in these lessons you've learned how to measure your pace, you know how far you can hike in a day, you know how long your pace is. We've also taken a look at contours, topographical maps, so you've got a sense of relief, so you know whether you're hiking up a hill, down a hill. Not that you couldn't figure that out yourself, but at least you can plan. One of the problems that Kronk and Grunt are going to have is knowing which way to head. We could direct them to go towards the North Star, not a problem, as long as the evening was not cloudy. We could say go towards the sunrise or towards the sunset. Again, not a problem unless it's foggy or nighttime. We still need some sort of sense of direction. That's where this next thing, the next step comes in. A couple of thousand years ago, quite a few thousand years ago actually, the Chinese discovered a rock. The rock we now call magnetite. And if they discovered that if you took a piece of this rock, it's got to be a weird shaped piece of rock, a long shape, suspended it from a string, it would always swing around and point towards the North Star. They considered it quite magical. They then would take this string, put it, say, on the yard arm of their boats, and they would use that to guide themselves. This is the first time that boats could leave the shore with any confidence, because they could leave sight of land, always knowing where north was. They could sail at night time because they could tell where north was. They could even sail through the fog because they always know where north is. This is the basis of the modern compass. They learned very quickly that if you take the magnetite and rub it on metal, the metal itself becomes magnetized and it will point towards the north. This next demonstration shows you how a compass works. What we're looking at here is a beaker containing water and a little bit of soap. The arrow is pointing towards the north. I checked that out with a compass. I'll just show you. I don't know if you can see it or not. There's the compass. You see it's pointing north. The red part of the compass is pointing north. The way we're going to do that is by taking this pin right here, and I'm going to be stroking it with the lodestone. I'll just turn it over here. Okay, if all goes well, we've now magnetized that. Now we're going to take the cork, put the magnetized needle on top of the cork. We're going to take that whole apparatus and we're going to put that inside or on top of the water in the beaker. Notice how the compass seems to point to the north. See, it's drifting around there, but always pointing in the north direction. This is a nice primitive compass. It would work very, very well. Now we could take a beaker of water, carry it with us wherever we went, carry a cork and a magnetized needle. Then, if we needed a compass, we just have to assemble it, sit there and wait for the cork to turn around and point to the north. Get an idea, dismantle it, and carry it away. Very, very cumbersome. A much better way would be to take that magnetized needle and instead of floating it on water, put it on a very sharp point, like a gem. And that's the basis behind modern compasses. The modern compass, the needle sits on a pin, and then it's enclosed in a housing to protect it so it doesn't fall off the gem, but also so it doesn't get damaged. Here are some examples of compasses we find. Now what we have here is a very simple, cheap little compass. Not very good for the things we want to do. This is a much better compass. It's very good for using on a map, not quite as good out in the field. This, the one I'm about to show you, is a nautical compass. And you'll notice the way it can float and pivot in any direction. And that's very, very good. But I want a compass that I can use both in the field and on a map. So I just bought this nice Sunto, S-U-U-N-T-O. I got it from Mountain Equipment Co-op. And I'll go through the parts in just a second. This is my compass. It's pretty nice. This is the one I got from the mech. First thing you should notice is the fact that it's on a plastic base. This is important for reading through it so you can see the details of the map. You'll notice also on mine that there is a lens for magnifying little objects that you might see on the map. Nothing special, but many of the compasses do have these devices. We also have a map scale, which is used to determine the distance you travel, and it's for the two typical types of maps. You have the 1 to 25,000 scale and the 1 to 50,000 scale. The direction of travel, the way you're going to be going, is indicated by this line up at the front, and notice there's a hole in the mirror for that, so you can always determine which way you're going. That's the idea behind it. Now these orienting lines are meant to line up against the map, so you're always pointing them in the north-south direction, or east-west, whatever. You'll see them in use later. The azimuth ring you can rotate to change the bearing. Again, we'll be using that a little later on, but that's the name of it, an azimuth ring. Notice this hollow red arrow here. That's called the orienting arrow, and it can be moved back and forth, and I'll explain how that works again, probably later on in this lesson. This is magnetic north. It's the red end of the arrow, not the black end, and the magnetic south is the black end. The little arrow you see in between is a clinometer. We don't worry about that. And my compass happens to have a sighting mirror right up here, and it's for use out in the field. We probably won't use it in the field. When you look at all of these compass faces, the card under which the compass needle floats, you'll notice they're all circles. This makes perfect sense. After all, the needle rotates around in a circle. So how do you decide how to mark up this circle? Well, a lot of this was done for us by the Babylonians way back when. The Babylonians thought that the sun rotated around the earth. They thought it took 360 days to rotate around the earth. We now know it takes 365. I guess the Babylonians lost 5 days. I don't know why. And they thought 360 is a magical number. So they put 360 degrees in a circle. This magical number appears elsewhere. You'll see there are 24 hours in a day, 4 times 6. There are 60 minutes in an hour, 6 times 10. There are 60 seconds in a minute, 6 times 10. The magical number keeps reappearing. But on the compass card, they decided that they would have 360 degrees. And the 0 or 360 mark, they're the one and the same, would point towards the north. Perfectly natural. That's where the compass needle is going to be pointing. Therefore, the opposite of that would be the south, 180 degrees. So when you hear of someone saying they did a 180, they turned around and went in the completely opposite direction. To the east, now when you're looking at a compass, that's to the right. To the east, they figure that's halfway between 0 and 180, that would be 90 degrees. And to the west would be 90 plus 180, which would be 270 degrees. They subsequently went ahead and renamed all of these marks. They decided they would divide it up a bit more just for our convenience. So halfway between north and east is northeast, and it's at 45 degrees. Halfway between south and east is 135 degrees. Halfway between south and west is 225 degrees. And halfway between north and west is 315 degrees. Each of these degrees is divided into minutes. There are 60 minutes in a degree, just like there are 60 minutes in an hour. Okay? The 60 minutes, or each of those minutes, can also be divided into seconds, though that's getting pretty small. We probably won't do that. I took my brand new compass down to Quinitza Park, down in Prince Rupert. Embedded in the pavement is a large arrow that is supposed to point to the north. So I thought I'd take my compass and put it beside the arrow and see exactly what's what. Much to my surprise and disappointment, my compass did not point in the same direction as the pointer in the concrete. What's going on here? Do I have a faulty compass? Did they perhaps install the arrow in the concrete inaccurately? Let's find out. The reason for this apparent malfunction in the compass is the fact that the compass needle doesn't point to the North Pole, that mythical place with the barber's pole at the top. It actually points to a place called the magnetic north. The Earth is magnetic, and the reason for it is the magma, the liquid part under the Earth's crust, is flowing around in circles, great big circles. It's kind of like water boiling in a pot. It comes up and turns around into convection circles. And of course the magma is very rich in iron, which is somewhat magnetic. So the tops of these convection circles come near the surface of the Earth up at the magnetic north. As a result, your compass pointer, your compass needle, points to that spot. Now, that shouldn't be a problem, except this magnetic north, presently located northwest of Ellesmere Island, moves. It moves at about 41 kilometers per year. So when you're looking at a compass, the pointer is pointing towards a moving magnetic north. So we've got to deal with this somehow. There are two ways of dealing with this issue. The first is the more difficult, but it's the best. Now, if you'll turn to a topographical map, such as this one I have for Port Essington, you'll notice on the right-hand side a little diagram that looks like this. Now, this represents the declination for this particular map. Okay. TN stands for true north. The star represents the North Star, or perhaps where the imaginary barber pole is located. To the left is the grid north line. This indicates the number of degrees the vertical line, the longitude, are off. I'll hopefully explain why this happens in the next lesson. To the right of the true north line is the magnetic north line. In this case, the magnetic north is 26 degrees. The little zero right there represents degrees, and 48 minutes. There's that little slash is minutes. Okay, beneath the line it says in bold print, where are we? Down here, that this measurement is the mean or average declination in 1980.
Now we know that it has moved since then. Below this it says that there is an annual change decreasing 7.7 minutes. It is now 2014 and the map was printed in 1980. Therefore, we are reading this map after 34 years of movement of the magnetic north. Okay, let's do the math now. If you recall, we said that the map was printed 34 years ago. That's where the 34 comes from. Okay, and for each of those 34 years, the annual change was 7.7 minutes. The little dash means minutes. And it's going to be a decreasing change. You've got to keep that in mind. So we've got 34 times 7.7 minutes gives us a total of 261.8 minutes. That's how much deviation occurred, right? 261.8 minutes. We never measure in minutes. Not when they're such big numbers like this. We measure in degrees. And there happens to be 60 minutes in a degree. So if we divide 261.8, that number there, by 60, that will give us an answer of 4.36 degrees. So we've started out at 26, now we come back at 4.36 degrees. That's the deviation. However, notice that's in minutes, the 48 minutes. It's not in decimal degrees. So we've got to convert the 0.36 degrees back into minutes, just the 0.36. So what we do is we take the 0.36, multiply it. This time there we divided. Now we're going to multiply in order to change just that part back, the degrees there, back into minutes. And we discover that that part, 0.36 degrees, is equal to 21.6 minutes. So overall, our deviation, based on just the change in time, 34 years, is 4 degrees, 21.6 minutes. We'll change that to we'll change that to 22 minutes. Keep it simple. So our declination of the true north, there's true north, TN, our declination right there is 26 degrees, 48 minutes, minus, it's going to be minus because it's decreasing, 4 degrees, 22 minutes. So 4 from 26 gives you 22. 22 from 48 gives you 26. So our declination of true north is 22 degrees, 26 minutes. But that hasn't accounted for the grid north deviation. Grid north deviation is a deviation caused by mapping techniques. We'll talk about that more when we get to the study, or get to the longitude stuff. Our grid north deviation, if we read up here, is 1 degree, 1 minute. So our final deviation is 22 degrees, 26 minutes, minus the 1 degree, 1 minute. That gives us a final deviation of 21 degrees, 25 minutes. The easiest way to find the deviation of the compass is actually to Google look for declination, and in my case I look for declination Prince Rupert. And I found 2 sites, there are many more, but 2 that sort of caught my attention. They are the following. When I looked at this site, I was quite surprised to find that the magnetic declination is 19.4 degrees east. Okay, I guess I was off. I don't know why. Now let's look at the airport declination. You'll see there it's 21.1 degrees east. The only way I can account for this is the fact that they were taken at different times under somewhat different circumstances. and the calculation's probably more accurate than mine because that's a very, very old map. So I've decided to take about 22 degrees deviation to the east as my standard, and I'll fix my compass up with that.
Here's my compass. And you'll notice that there is a hollow red arrow. Right now it's pointing towards the north, right here. Now, on the back of this compass, right here, you see there's a little screw hole. This is for adjusting the declination. On the lanyard, there's this dinky little screw mechanism. What I have to do is I have to take this and turn the screw so that that red arrow moves over to about 21 degrees, 25 minutes. Well, it so happens it's going to have to be about 22 degrees, I think, because it's very crude. Okay, I'm turning it now. I don't know if you can see. I'll turn it a bit so you can see as I turn it, it moves. And it looks like it's almost there, 20 odd degrees. Bit more. Yep, that's about 21, 22 degrees. Okay, notice now that that N on the white azimuth is pointing towards the arrow here, or towards that pointer, but the hollow red arrow is no longer pointing there. So now I want to take this compass back down to Quinitza. Let's see how accurate it is. When I went back to Quinitza to test my new compass, now it's got declination added, I expected it to be dead on. I was somewhat disappointed because it wasn't, not quite. It was close, but not quite. The only reason I can think for this anomaly would be perhaps there's a lot of iron in the ground, perhaps in the concrete, or perhaps my declination calculations were a little bit off. Okay, I think we're pretty well done with the compass now. You'll probably not do anything with the compass for a bit. We're going to be moving on to longitude, but there is an assignment whereby you have to find the declination for your particular community. You can do. I would encourage you to use both methods: the long, tedious way, doing the calculation from a topographical map, and the easy way. Try Google Maps. They'll give you all the information you need. But if you've got a compass that can be calibrated, do it now. It'll save you all sorts of trouble later on. Right? Talk to you soon. Right. Bye-bye.